The goal today is to finish talking about exceptions to the octet rule, molecular polarity, and then we're going to start building. Yay! Okay, so octet is, of course, just a kind of guideline. It's a guideline, not really a rule. So anything with this, like I told you guys yesterday, so phosphorus, sulfur, chlorine, argon, and forward, they have access to D block electron or D block orbitals so that they can shove the extra electrons in there. That's the only way they can expand octets. So first step in any drawing is what? Count them. Count them. So how many do we have?
48.
So you did 6 for sulfur plus 6 times 7. So is that 48?
42.
42 plus 6, 48. Sounds great. Okay. So who's the center? Sulfur. And then what do you do? Right? So give it 1, 2, 3, 4, 5, 6. Fluorines all the way. The only hard part on this, because this part is easy, I think, drawing it and then putting your electrons everywhere. First of all, do make your electrons clear on the AP exam, and if you don't put the electrons, you don't get credit at all for your structure. So, you know, make sure you're following the 48 guideline here. So you can count by 8s, and you can see that you should have 48. 8, 16, 24, 8, 16, 24, 24, 24, 48. Okay? So that's our structure. Can you imagine what this structure looks like in terms of its molecular geometry? No, definitely not 2D.
The middle.
It's only 5.
It looks like a pyramid.
What is the pyramid's base? The base, of course, is in the middle, okay? So our thing is that if I'm sulfur, okay, what's the shape of the pyramid? The base? Is it trigonal or is it square? It is square. Okay, so here's what it looks like. I actually thought I had it built by now. So, okay, well here, let's look at this one. Do you see that this one has a triangle in the middle? See it? Yeah, the silvers are a triangle. But it's got a pyramid on top and a pyramid on bottom. Right? So this is trigonal by pyramidal. Yes? You see it? So how is this one different? It has 4 in the middle. So it's not trigonal, it's square by pyramidal. Square by pyramidal. Because there's a square in the middle versus a triangle in the middle. Okay, well I think when you handle these, it'll make a little bit more sense. So here's kind of what it looks like. It looks like, so we're going to draw silver. I'm going to try to draw it 3D for you, okay? So try this with me. And your F's, fluorines are out to the side like this. And you kind of just make a, kind of like that's like a flat plane, right? And you got a fluorine up top. And these guys all connect to that fluorine up top. And then you have one down low. And these fluorines all connect kind of. Doesn't that kind of like a good square pyramid? Bipyramidal? I'm an artist. I really try. Okay, so basically that's what we're looking at on a 2D plane. This is a 3D plane. Do you think that this overall molecule, okay, so think of the difference between sulfur and fluorine's electronegativity. Where would the electrons be shifting towards in that covalent bond? Towards fluorine, for sure. Like, it's the most electronegative. That's without a doubt. So in this case, you could draw dipole moments in every single. Hey, just go to the back and then behind Mr. Aldridge's room. You could draw all these dipole moments pointing to every fluorine, right? Well, that's tedious. But if you think about it, we know the electrons are pointing up, out, 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 down equally, right? So there's like an equal halo of negatives around it. Is there an unequal distribution of electrons?
No.
No. So would you consider, so it's, someone call that equal distribution of electrons. Would that be polar or non-polar? Non-polar. Non-polar means there's not opposite ends. Equal distribution, okay? So this is a non-polar molecule. Despite the fact that it has what kind of bonds? Polar covalent bonds. The geometry allows for the cancellation of the polarities because there is an equal distribution across the whole entire field here. So there's an equal distribution overall of the polar covalent bonds. And the geometry allows for them to kind of cancel each other out, making the overall molecule nonpolar. So the nonpolar covalent bonds, polar covalent bonds can't make a nonpolar molecule because of the geometry. That is the main point of this. Okay? And it's expanded octet. It's disobeying the octet rule. All right, so let's do xenon tetrafluoride. Xe, so you start that one and think about what the shape will be. I have a whole list of shapes we're going to go through with bond angles in just a second too. So xenon tetrafluoride. How many electrons do we have?
32.
So xenon is 8 plus 28, 36, right? So xenon is 8 plus 4 times 7, so that's 36 valence electrons. So your center is definitely xenon. I need some space on. I love drawing these things. So I do my free time. Okay, so then what's next?
Draw the four fluorine bonds.
Okay, you can draw them as like a T or as an X, kind of like this. You just need to have a kind of more of a symmetrical model. And then make sure everybody has octet. And in this case, everybody has octet once I'm finished here, right? How many electrons are on my structure?
32.
32. So what do I do with my extras?
Stick them on xenon.
Right. The rule is if you have extra electrons, you do not put them on the exterior, you put them on the central atom, because the central atom has the ability to push the bonds around until they get to a favorable shape where there's less repulsion and more stability. So these electrons I'm just going to stick on the sides here. And sometimes I'll even tell you to circle them, because sometimes I can't see your dots, people. So circle them for me so I'm very aware. So we actually have 6 electron domains. So what do you think electron domain means, according to what I've just said? Electron domain.
6 places where there are electrons.
Thank you. 6 places where there are electrons. I'm not specifying lone pairs or ligands themselves. In this case, there are 4 ligands. Did we get to this term yesterday? Okay. I've done this exact same thing in honor of and you guys, and I can't remember what I've said in which class now. So 2 lone pair, because there's 2 lone pair on the central atom, and there are 4 ligands, meaning actual atomic attachments. But overall, 4 plus 2 is 6 electron domains. Okay, so the 6 electron domains are actually what we're concerned with in terms of figuring out the geometry. So these lone pairs here are incredibly negative. They really don't like to be close to these 4 bonded pairs. So they're going to shift in a way to allow them to have most space. Thank you. So this need the most space. So thinking axial, which is up and down, which is in this case the green and white, versus equatorial. We have to arrange 6 things in a favorable manner. What's the bond angle between the axial and the equatorial? 90. In this case, what's the bond angle between these equatorials?
120.
120. Because in a okay, that's kind of supposed to look like it's coming out of the board. So in a trigonal bipyramidal example, this is definitely a 90-degree angle, but then between here, here, and here, that's a 120, okay? The most favorable position for a lone pair would be the most space, like an equatorial position, because there's 120 versus a 90, and there's less repulsion. But we don't actually have that case here. We have a square pyramidal, a square bipyramidal kind of arrangement. These lone pairs are actually going to have, I mean, everybody's going to be 90. You have a square in the middle, and then an equatorial, because it's 90 here and it's 90 here. So there is no real favorability. But we have to be able to describe this as an appropriate shape. This actual shape, if you're considering the actual shape without the lone pairs, is called square planar. And there's a 90-degree angle between all the bonds. You are going to memorize these. But it makes spatial reasoning is going to be very important here. So you have to really try to conceptualize this. So what happens is xenon's in the middle. I'm trying my best to draw these 3D for you. Fluorine is on each. This is a flat plane, okay? So flat plane. And there's a big lone pair up, and there's a big lone pair down. And so that makes a flat square because these lone pairs, it's not that they have more space, it's just they need to be as far away from each other as possible. So they take the opposite axes. And then the equatorial region is where the fluorines exist. So using the term equatorial and axial is going to be kind of key in how you describe certain things. Okay? The shape kind of makes, I mean, the geometry part makes sense. Okay? All this geometry is based off VSEPR. VSEPR is, I'm going to go through that in a second. Ready? VSEPR. Let me show you the VSEPR first. Okay. VSEPR, valence shell electron pair repulsion theory, and it's how we actually determine the geometries. There are actually 3 bonding theories, but they all explain things, one part of bonding really well, but then they have a limitation on another part of bonding. So we do agree, all of them are true to an extent. but we do have to know all of them. So the VSEPR theory is when you learned in honors chem. Valence shell electron pair repulsion. So basically the valence shell of electrons repel other valence shells of electrons, bonding pairs, lone pairs, and they morph themselves into a shape. I have a video for you. I think that will help with seeing how the spatial patterns change with the repulsion of the electrons. Basically, we want to have a large distance between bonded pairs, so the maximum distance between bonded pairs, and that's why we have tetrahedral, trigonoplanar, trigonopyramidal, all these different shapes, because different shapes allow for the maximum distance between certain types of electrons. So the lone pairs are going to spread out, which is really what's causing these shapes to be distorted as so. So we kind of just went through that and that. But we've been calling this molecular geometry. We're going to call something else electron pair geometry in a couple minutes. So this VSEPR theory goes along with molecular geometry. We remember some of this from honors chem. It's more recent for some of us. If you skip a year, you got to look at this a little bit more often. But I think it'll come back to some. I'm optimistic. So I'll watch this video in a second. Just turn off my music. Okay. Turn off Spotify. Can I show the video? I'll give you a second there. Okay, so this might help a little bit. Oops, what am I doing? This needs to come on.
What is the shape of a molecule? Well, a molecule is mostly empty space. Almost all of its mass is concentrated in the extremely dense nuclei of its atoms. Its electrons, which determine how the atoms are bonded to each other, are more like clouds of negative charge than individual discrete particles. So a molecule doesn't have a shape in the same way that, for example, a statue has a shape. But for every molecule, there's at least one way to arrange the nuclei and electrons so as to maximize the attraction of opposite charges and minimize the repulsion of like charges. Now let's assume that the only electrons that matter to a molecule's shape are the outermost ones from each participating atom. And let's also assume that the electron clouds in between atoms, in other words, a molecule's bonds, are shaped kind of like sausages. Remember that nuclei are positively charged and electrons are negatively charged. And if all of a molecule's nuclei were bunched up together, or all of its electrons were bunched up together, they would just repel each other and fly apart, and that doesn't help anyone. In 1776, Alessandro Volta, decades before he would eventually invent batteries, discovered methane. Now the chemical formula of methane is CH4. And this formula tells us that every molecule of methane is made up of 1 carbon and 4 hydrogen atoms. But it doesn't tell us what's bonded to what, or how the atoms are arranged in 3D space. From their electronic configurations, we know that carbon can bond with up to 4 other atoms, and that each hydrogen can only bond with 1 other atom. So we can guess that the carbon should be the central atom, bonded to all the hydrogens. Now each bond represents the sharing of 2 electrons, and we draw each shared pair of electrons as a line. So now we have a flat representation of this molecule. But how would it look in 3 dimensions? We can reasonably say that because each of these bonds is a region of negative electric charge and like charges repel each other, the most favorable configuration of atoms would maximize the distance between bonds. And to get all the bonds as far away from each other as possible, the optimal shape is this. This is called a tetrahedron. Now, depending on the different atoms involved, you can actually get lots of different shapes. Ammonia, or NH3, is shaped like a pyramid.
Okay.
Carbon dioxide, or CO2, is a straight line. Water, H2O,
What shape is that? Bent and.
is bent, like your elbow would be bent. And chlorine trifluoride.
Can you tell what shape that is? No? It's a T. It is literally called T-shaped. Super creative, people. Okay, why would that be T-shaped? What would be back here that's invisible to us? How many lone pair? Okay, so think about a tetrahedron, right? A tetrahedral. If I take off one lone pair, what shape is that? What shape is that?
Trigonal.
Pyramid. Trigonal pyramid, right? So it's not one lone pair. So what do you say?
3.
Nope. 2 lone pairs. Okay. The reason why is because think of this. What shape is this again? Trigonal bipyramidal, right? If I take off one lone pair, okay, you can see that we have this funky shape. Watch up here. Watch what it does. Ready? Look. What shape is this? Seesaw. This is seesaw. This is called seesaw. You read this in your packet? Okay, we're super creative people. Okay, so that is seesaw. That's one lone pair removed from a 5-electron domain system. Second electron, so I removed it from the 120 region because that's a lot of space, and a lone pair likes a lot of space. I'm going to remove another one from the big equatorial region, if I can. Okay. And so these 2 lone pairs here have a large amount of space to themselves. So what's that shape? T-shaped. So remember, that's from a 5-electron domain system. The atomic arrangement is a T-shape. The molecular, so we call that we call the T-shape one molecular geometry. But if you consider the lone pairs here as well, we call that electron pair geometry, and it's still trigonal bipyramidal because we were considering them as an extension. So we're going to distinguish between those two in a second.
Or CLF3 is shaped like the letter T. Remember that what we've been doing here is expanding on our model of atoms and electrons to build up to 3D shapes. We'd have to do experiments to figure out if these molecules actually do have the shapes we predict. Spoiler alert, most of them do, but some of them don't. Now, shapes get more complicated as you increase the number of atoms. All the examples we just talked about had one obviously central atom, but most molecules, from relatively small pharmaceuticals all the way up to long polymers like DNA or proteins, don't. The key thing to remember is that bonded atoms will arrange themselves to maximize the attraction between opposite charges and minimize the repulsion between like charges. Some molecules even have 2 or more stable arrangements of atoms, and we can actually get really cool chemistry from the switches between those configurations. Even when the composition of that molecule, that's to say the number and identity of its atoms, has not changed at all.
Photons and matter interactions. Okay, so does that help a little bit with your spatial reasoning? Okay, let's start drawing these things now. Okay, we're going to start about molecular polarity. Pull out that sheet, page 26, 28 in your packet, and I'm going to show you the beauty of drawing these babies. So I'm going to need to find that sheet real fast. I think it's right here. It looks similar to this. Find it for me, because we're going to draw these. We're going to think about the bond angles. Alright guys, so my drawings are here, and I'm going to give you another drawing over here. Yeah. Do I have your packet? Did you leave your packet? Oh, your packet the bonding one? You should have your bonding one. You turned in your atomic structure one. Yeah, okay. I was like, hold on, I don't think I took that up. Okay, so this shape is definitely linear, right? Give yourself a sketch. I left the boxes open for you guys to sketch. That's the very last page in your packet. So if you have 2 pairs of electrons that are shared, we call those bonding electrons. 2 0 unpaired shares, unshared pairs. That would be like 0 lone pairs. We just have a linear structure. Give me an example of something that would have a linear structure. Carbon dioxide. What else? Maybe like something like HCl. Great. It's one bonded to another. Now we don't definitely know the polarity of it, but like carbon dioxide is definitely polar or nonpolar. Because it's equally distributed on either side, that's nonpolar. But HCl would be polar because we don't have an equal distribution on left and right. Chlorine took out the most electrons. So that one doesn't have like a distinct polar or nonpolar. There's always variability. But the angle is 180 because between the 2 sides, that's like a semicircle, right? So 180 degrees. Okay? Who does not find their packet? Do we have the sheet? So next one. we have is one where you have 3 electron domains, but the electron domains can change to be bonded pairs or non-bonded pairs. So this is kind of the general arrangement, and you can see that these just have electrons there. They're not showing them being bonded to anything or being lone pairs. They're just electron domains. So if you have 3 shared pairs, meaning 0 lone pairs, you are a flat structure, evenly distributed away from each other, called trigonal planar. So 3 trigonal planar flat. And that angle between each of your ligands is 120 degrees, because 360 divided by 3 is 120. The bonding ones are not hard on some of these. Are we okay so far? What would be a good example of something with a central atom and then 3 ligands? Lewis, you drew one yesterday. Not that one, because that one has a 4th lone pair on the top. So when you came and did on the board, we're on trifluoride. Okay. So that would be a good example of a trigonal planar one. That's an exception to the octet rule. Now, if I take away the lone pair, if I take away the bonding pair, and instead of the lone pair there, it's going to look like this. And you can see this E is supposed to represent a huge lone pair. Well, instead of being trigonal planar, it's going to be bent. So another word for bent is angular. Bent is more commonly used in modern day versus thin. This is like probably the 90s or 80s. This is an old worksheet. But you can see that the angle now, it says less than 120. Why? Why would it be less than 120?
Because the pair of electrons push
Yeah.
bonds harder.
So they repel, like the VSEPR theory says. That's valence shell electron pair repulsion, pushing the angle down to a more skinnier angle, so less than 120. So that would be a little bit more high energy, less stable. Okay, now we've got 4 electron domains. 4 electron domains meaning the most simplest of them would be tetrahedral, and that's one that we're very familiar with. Oh, sorry, example for this one, sulfur dioxide. That bent one I just went through. So tetrahedral, what's a good example for tetrahedral? Say again? I heard it. Starts with the M. We just talked about it in the video. Methane, thank you. CH4 would be a good example of that. And if it is the same ligand on each of the same exact bond type ligand, would that structure overall be polar or non-polar? If there's an equal bond, north, south, east, west, up, down, side, side. Non-polar, due to the fact that there's an equal distribution of electrons. If it wasn't the same exact bond on each of those ligands, then you couldn't say it's definitely non-polar. You'd have to look at the electron arrangement, electronegativity. So that angle is 109.5. You need to memorize that. 109.5. Okay? And then now you can kind of see the sequential dropping of a ligand to make it a lone pair and see how does it change the actual bond angle or the shape, right? So if I take away the top ligand and make it a lone pair, this lone pair is repulsive, so it's pushing the angles that are between each of these remaining ligands, pushing them together. So it gets less than 109.5. We actually know the angle. It's approximately 107.5. So make sure you're running 107.5. With that, we now call this a different, so we went from tetrahedral molecular geometry to what? Pyramid. Trigonal pyramidal, right. That's trigonal pyramidal. And a good example of that would be what, Lewis? Ammonia. So that's one we're very familiar with. You guys okay? Sketching-ish. And really the details are more important. You guys will see these images like these in the 3D shape in a second. All right, so then what do you think the shape's going to be when you drop another alone pair? So we went from tetrahedral, right? So trigonal pyramidal to or bent, right? So bent, angular, same thing, but bent is more commonly used. So we have a big lone pair, and 2 attached atoms. What is a good example of that? Thank you. Water. This is H2O. Okay, so we went down from 109.5 to 107.5 with a drop of 1 lone pair. With a drop of a second lone pair, ligand to make a lone pair, it's actually way less than 109.5, and it's actually 104.5. It looks like it's going to be a 2-drop, but it's actually a 3-drop on this one. So 104.5 is an example for water. It might vary just a little bit depending on the size of these atoms. Like H's are really small, so that angle is 104.5, but it might differ if they have different atoms. So that's bent again. Okay, and then if I drop a third one, then it actually is very similar to one of our first examples, like linear. But an example of this would be like hydrofluoric acid, where you have your lone pairs like that. This one we don't see too often because that's not a very complex model, and you can see the angle between them would be 180. That's as far as you can get away from another one, right? You can't really get any farther away. Yeah.
There's 2 bends.
Yeah, there's 2 bents. Bents with 3 electron domains, where 1 is a lone pair, and there's bent where there's 4 electron domains, where 2 of them are lone pair. What's the difference in angle though? What's the first bent one?
104.5.
Right. So they're both bent. It's just their angles are different based on their electron domains. Like sulfur dioxide, right here. It's like S with a lone pair and then O2. That's a good example. All right. So these are the simpler ones. Okay. These are the terms we've used before. These are the ones that are bigger. These are expanded octet and more. Okay. So 5 electron domains. I'm giving it all to you right now. Okay. 5 electron domains. If I just simply have 5 electron domains, 0 lone pair, I'm going to take on the appearance of. I'm going to show you from here because I think it'll help. This guy is trigonal bipyramidal. So trigonal in the middle, bipyramidal top and bottom. You see the trigonal bipyramidal? Okay. So that's what this one is, and you can see the angle between axial and equatorial is 90 degrees. Axial and equatorial angle is 90, but then between the equatorial region, between all those ligands, they take up 360, but they're divided by 3, so what's their angle? So what's 360 divided by 3? 120, so it's like 120 here, 120 here, and 120 here. So between the equatorial region, they're at 120 from each other equatorially. Okay, so then I drop down. So all I'm doing is simply taking a ligand off and replacing it with a lone pair. But what's the most favorable place for that? It's going to be the place where the lone pair has the most space to spread out. That's not the axial region. Axial is at a harsh 90 degrees. It's not going to be happy there. So it has to be removed from the equatorial region so that the lone pair has all this space to play and spread out. So that's why you can see it's being taken off the back side of this equatorial region. And you'll see the angle here. So seesaw, it says it's 120 and 90. It's actually a little bit less than that because what can you imagine this lone pair back here is doing? Repelling, it's pushing, right? It's pushing this angle and the other axial one a little closer to each other. It's not much, but it's less than 90 degrees on the axial regions. And then the equatorial, they've been pushed also closer to themselves. So it's also a little bit less than 120, but we don't know the exact one. So that one's seesaw, and I showed you how it's seesawed, right? That one makes sense now. Take off another equatorial region because that's where the most space exists, and you get T-shaped. Okay, so T-shaped, there is no other angle. It has to be pretty much 90. It can be a little less than 90, but 90 is what they say because once you get 2 lone pairs there, they're actually kind of countering each other, and one will push the axial down and the other one will push it back because they're kind of against each other almost in that case. So that one's 90 degrees, and you guys are going to do examples of these in your lab. So take off another one. Where do you think it's going to be removed from? Axial or equatorial? Again, equatorial. In this case, it doesn't matter because everything's at 90. But if you can take off the equatorial, it actually does alleviate some of the repulsion in the middle because you'll have 3 electron lone pairs in the middle where they'll get to spread out 120 from each other. And then they'll be at 90 from the axial. So that's going to take on a linear shape. This is linear. It's not a 2 electron domain linear. It's not a 4 electron domain linear. It's a 5 electron domain linear. So in this case, 3 lone pairs are in the equatorial. So lone pairs are equatorial. and the two atoms are axial from each other. So 180 is what they describe as the atomic bond angle from the atoms of each other. Does this make sense so far as we're walking through it? It's memorization, but if you think about it, it's not memorization. It makes sense. Okay, last one, 6 electron domains, which I don't have built right now. But 6 electron domains is going to be the square, what was our example? Sulfur hexafluoride. So sulfur hexafluoride was an example we did earlier. And we drew that square in the middle, and we said that there was like a pyramid on top, and then a pyramid on bottom. You can kind of see it. Okay, so that one's square pyramidal is another way of saying octahedral. So square pyramidal is octahedral. And there is no choice. It's 90, 90, 90, 90, every which way you go. So that's a pretty repulsive structure because there's so many bonds in such little space. It's probably very high energy, high instability. Then you take off one bonding pair and you make it a lone pair. When you make a lone pair, we don't really have a large option of where to put this lone pair, but the best case scenario is to put it as far away from other bonds as possible, or everything's at 90 degrees. So where do you put it? You choose an axial region. So you can see that this one is put axial because the axial at the end very well could be farther away than the other ones because we can push those away if we need to. So this is still square. Oh, sorry, this is square bipyramidal. Let me go back up to the 6th one. That's square bipyramidal. Sorry, I drew it bipyramidal. I just didn't write it up here. This is just square pyramidal. As you can see now, it looks like this. Okay, because you'll have your atom in the middle, and then your 4 atoms here, and then 1 atom up here. And then there's a big lone pair on the bottom, but you don't consider the lone pair as a part of the structure. It's just what happens as a result of this repulsion. And then, last but not least, we have one like we did earlier. Which one was square planar we did earlier? Warm up. What was the name of it? Xenon tetrafluoride, right. So that was a good example, and you can see that it has its square planar shape in the middle, and then the lone pairs are opposite of each other because they need to be as far away from each other as possible. So lone pair are, again, axial because of their repulsion for each other. Whew. So that's that. The bond angle ones are going to be kind of anything that you're trying to think about, but I think that if you look at the structures more often, try your best to draw as many of those structures as possible. That way you might actually remember what they look like. So when you draw them again, you're like, ah, this looks familiar, or no, this is totally wrong. So I'm going to have you guys start your lab first, and I'll kind of pick up at the end with bond. Turn to page 13 in your packet. 13. So what you don't finish today, you'll have time to finish Monday. I'll tell you what we'll do Monday. Monday, this is honors Chem. What's honor? Monday, you'll have about 30 minutes to finish your molecular modeling building, and then you're going to start a pre-lab for inquiry lab. And you'll start some reading on your next MSMI reading. But today, I want you guys to take about 30 minutes-ish to draw structures and build them. I prefer you to draw all your structures first and then build them all together. But if you are bored and you need to get on hands-on, the structures at the back you can you can draw and build, draw and build, draw and build. Every time you build, though, I have to check it off, okay? And we'll talk about it. So, this is a lab part. This is like a single partner for this activity, okay? So, choose a friend, take a friend. I have one group of 3 because I'm missing Kevin. But I do recommend you start drawing on like a separate sheet of paper because that little bitty piece of paper is not going to be enough for you. Okay? See you in 30 minutes. Knock us out. I'll come help you build if you need it.